Hello, this is video number 17 on my single variable calculus 2. In this video, we're going to talk about trapezoidal and Simpson's rules. So first, what is the trapezoidal rule? In order to evaluate an integral, we have discussed lots of different analytic methods of evaluating integrals. We usually can't evaluate an integral. So how do we find an integral without actually evaluating it? How do we approximate that? Well, one method that you have learned is using Riemann's sum. So if you take an integral from a to b of a function, you can take Riemann's sum of this function, and that gives us the area underneath the graph of the function. So that's one technique. But those are going to give us approximations of integral which are not necessarily very good approximations. So in this video, we're going to talk about two other techniques that give us better approximations in general. So here's what we're going to do. We are going to take the interval and divide it into smaller pieces. So let's say the interval is divided into 4 sub-intervals. So we are going to have 5 points here, x0 all the way to x4. And then we are going to, instead of evaluating the area of rectangles here, we are going to evaluate the areas of these trapezoids. So we have a trapezoid that is obtained by connecting the endpoints here. So if we connect these 2 points, if we connect these 2 points, and if we connect these 2 points, we are going to get a trapezoid. We're going to get, in fact, 4 trapezoids. And then we are going to add the areas of these 4 trapezoids, and that gives us an approximation for the area of the graph on the area of the region underneath the graph. Let's find the area of each of these trapezoids. So the first trapezoid has 2 bases. The first base is f of x0. The second base is f of x1. Then we have to take the average of the 2 bases and then multiply by the height. So notice that the height is this one. Area of a trapezoid is base 1 plus base 2 over 2 times height. So this is the area of the first trapezoid. Now we can do the same thing and find the other trapezoids, area of these areas of the other trapezoids, and then add them up. So if we do that, the integral from a to b of f of x dx is going to be approximately, all of these areas are going to factor delta x over 2 because they all have the same height, delta x, and they all have over 2 because we take the base 1 plus base 2 over 2. Now we're going to have to multiply by the sum of the 2 bases. The first one gives us f of x0 plus f of x1. So this is for the first trapezoid. The second trapezoid gives us f of x1 plus f of x2. So this one is for the second trapezoid. And we do the same thing for the next trapezoid all the way to, let's say there are n trapezoids. So what we do is we take the interval from a to b and we divide it into n sub-intervals. So we have x0, x1, xn minus 1, and xn. So the last one would be f of xn minus 1 plus f of xn. So this would be for the nth trapezoid. Now, if we add up all of these, we are going to get delta x is b minus a over n. We have a 2 at the bottom, so we get b minus a over 2n. And then we get f of x0 plus, there are 2 f of x1s, so we get 2 f of x1. Then we have 2 f of x2, and we have 2 f of xn minus 1, but we only have 1 f of xn. This sum is called the trapezoidal approximation that I have written it here. So the integral from a to b of f of x dx is approximately b minus a over 2n times this sum. So what you really need to remember is these coefficients that are 1, 2, 2, 2, everything is 2 except for the first one and the last one. And of course we have also a b minus a over 2n. And this is an important formula that you need to remember, and that's what you use in order to approximate an integral using the trapezoidal method. So next thing we're going to do is we're going to do one example on this. So what is the approximation for this area underneath the graph of 1 over x from 1 to 2 using the trapezoidal rule? So what we're going to do is we're going to take the interval from 1 to 2. We are going to divide it into 3 pieces because that's what they told us. So we are going to divide this into 3 pieces. So delta x would be basically 1/3. So the function is 1 over x, b is 2, a is 1, and n is given as 3. So we go 1/3 to the right, so that would give us 4/3, 5/3, and 6/3, which is 2. So the integral from 1 to 2 of 1 over x dx is going to be approximately b minus a over 2n times f of x0, which is 1 over 1, plus 2 times the next one, which is 3/4, because it's 1 over 4/3, plus 2 times the next one, which is 3/5, and then plus the last one, which is 1 over 2. So this would be an approximation for the area underneath the graph of 1 over x from 1 to 2. Okay, so the next thing we're going to do is anytime we have an approximation, we would like to know what is the error of that approximation. And this formula gives us an upper bound for the error of the approximation. So this error, which I denote by E sub t, is the absolute value of the difference between the actual value of the integral and the trapezoidal approximation. So if you take that error, then the error is always going to be less than or equal to k sub t, where k sub t is the maximum of the absolute value of f double prime over 12n squared times b minus a cubed. So this tells us that as you make n large, your error is going to become small of order of n squared. So let's look at an example on this. Okay, so let's look at one example. Determine a reasonable value of n for which in approximating this integral using the trapezoidal rule, the error does not exceed 1 over 60,000. So the function that we are given is 1 over x, b is 2, a is 1. And the question is, what is n? We want the error to be less than or equal to 1 over 60,000. Okay, so in order to evaluate n, we'll have to figure out what is k sub t. So what is k sub t? That's the maximum of absolute value of f double prime. So we have to take the derivative of f. That would be minus x to the power of minus 2. So the second derivative of f would be positive 2x to the power of negative 3, which is 2 over x cubed. Now we will have to take the absolute value of this. Because x is between 1 and 2, this is positive, so I don't really need the absolute value. So what is the largest value of this expression? Well, because x is between 1 and 2, the smallest value of x is 1. Because it's in the denominator, the largest value would be 2 over 1 cubed. So that tells us that k sub t is equal to 2. Now, we know that the error is less than or equal to 2 over, we have 12n squared, so 12n squared, and then we have b minus a cubed, I believe. Yeah, so that would be cubed, although it doesn't really make a difference here because b minus a is 1 anyway. So we are going to take this. We have 2, which simplifies with the denominator. We get 1 here, we get 6 here. So we get E sub t is less than or equal to 1 over 6n squared. We would like this to be less than or equal to 1 over 60,000. So we are going to simplify 6. We get 10,000 on this side. So we are going to clear the denominators. We get 10,000 is less than or equal to n squared, which means n is at least 100. So the smallest value that we can use is n equals 100. So in other words, if I want to guarantee that my error does not exceed 1 over 60,000, I have to divide my interval from 1 to 2 into 100 intervals. Okay, so let's look at the next method of approximation of integrals. The next method is what we call the Simpson's rule. So what is the Simpson's rule? The Simpson's rule uses a different method of approximating the areas underneath the graph. So what we do is very similar. We are going to divide this into, let's say, 4 pieces. In the trapezoidal rule, we approximated each of these curves with a segment. Instead of doing that, we are going to approximate the curve by a parabola. So we're going to take 3 consecutive points here, and we are going to approximate that with a parabola. Let's say this is a parabola that approximates the curve. And for the next 3 points, we are going to use another parabola here. And then we are going to evaluate the areas underneath the graph of these 2 parabolas, and we add them up. And that would give us another approximation. This method is called Simpson's rule. This approximation is going to be a better approximation. So again, we take the interval from A to B, we divide it into smaller sub-intervals, x0, x1, x2, all the way to xn minus 1 and xn. And then we take every 3 consecutive points, in this case, this point, and this point. We draw one parabola, then the next one would be this point, and this point. And then we draw as many parabolas as possible, and then we take the area underneath the graph of each one of them, and then we add them up. Now, because I'm looking at 3 consecutive points, I would need n to be even. So I have to have n even to be able to draw parabolas for every 3 consecutive points. Otherwise, if you have one more term here, you can't really do anything with this last piece. Now, what is the formula? Now, it's a little bit more complicated to find this formula because you need to find the area underneath the graph of a quadratic. But it is possible, and the formula is b minus a over 3n times f of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3, etc. So the coefficients are 1, 4, 2, 4, 2, 4, 2, 4, and then the final one is 1. So the initial and the final coefficients are 1, and the in between, they start with 4 and they end with 4 as well. Let's now do one example on this one. We want to approximate this integral when n is equal to 8 using the Simpson's rule. So we have the integral, it goes from 1 to 5. So we have to divide this into 8 pieces. So our delta x, which is b minus a over n, would be 5 minus 1 over 8. So it is in fact 1/2. So we'll take this one, and then we have to divide this into 8 pieces. So this would be 4 pieces, and this would be 8 pieces. So each time we have to add 1/2. So this would be 3 halves, 2, 5 halves, 3, 7 halves, 4, 9 halves, and 10 halves, which is 5. So the integral from 1 to 5 of square root of 1 plus x cubed dx is approximately b minus a, which is 4, over 3 times n, which is 24, times, and then we have to evaluate function at these points and then include those coefficients. The first one is root 1 plus 1 plus 4 times root 1 plus 3 halves cubed plus 2 times root 1 plus 2 cubed plus 4 times root 1 plus 5 halves cubed plus 2 times root 1 plus 3 cubed plus 4 times root 1 plus 7 halves cubed plus 2 times root 1 plus 4 cubed plus 4 times root 1 plus 9 halves cubed. And finally, the last one is 5. So that would be square root of 1 plus 5 cubed. So this would be our approximation. Okay, so finally, the last thing we're going to have to talk about is what is the error in this case. So the error in this case is much smaller, and I will illustrate that with the next example. So if k sub s is the maximum of fourth derivative, in this case we have to find the fourth derivative, then the error would be that k sub s divided by 180 n to the fourth. So as n gets large, this quantity becomes smaller much more rapidly than if you had n squared at the bottom. So let's do one example on this. Determine a reasonable value of n for which, in approximating this integral using the Simpson's rule, the error does not exceed 1 over 60,000. This is the exact same problem that we just did, except that the method is going from trapezoidal to Simpson's rule. Okay, so we're going to have to find the fourth derivative of the function. So the function is 1 over x. We already evaluated the second derivative of this. The second derivative is 2x to the power of negative 3. So the third derivative is negative 6x to the power of negative 4. The fourth derivative is 24 x to the power of negative 5, which is 24 over x to the fifth. So its absolute value is itself, because it's positive, 24 over x to the fifth. Now this is less than or equal to 24 over 1, because x is between 1 and 2, and x is in the denominator. The smaller x, the larger the fraction. So that tells us that k sub s is equal to 24. So what we need is we need 24 over 180 n to the fourth times b minus a to the fifth to be less than or equal to 1 over 60,000, because that was the formula that we were given. So it's k sub s over 180 n to the fourth. So k sub s is 24, 180 n to the fourth, and then 2 minus 1 is just 1 to the power of fifth. Okay, let's simplify this and see what we get. So first of all, one of the zeros cancels here. We can divide this one by 6. We get 4. We get 3 here. We can divide this one by 3. We get 2 here. So we get 4 over n to the fourth is less than or equal to 1 over 2,000. Okay, let's clear the denominators. We get 8,000 is less than or equal to n to the fourth. So it's not very difficult to figure out what the value of n is, but you also need to make sure that n is even. So whatever you get, you have to make sure that you find the first integer that n to the fourth is more than 8,000, but it would also have to be even. If it is, let's say, 9, then you'll have to choose 10. Okay, so clearly 10 to the fourth, which is 10,000, is greater than 8,000. So this does work. Now let's test 9 to the fourth. 9 to the fourth is 81 squared. Let's multiply 81 and 81. So you get 81, 8, 64. You get 1, 16, 5, and 6. So that is 6561, and that is less than 8,000. So that means 10 works, but 9 doesn't work. So that tells us that n equals 10 is in fact the answer to the problem. But again, remember that this n must be even. So I am checking that it is even. If this were, let's say you found 11 is the first number that satisfies the inequality, then you would have to choose 12. So to summarize, what we learned here was basically two formulas for trapezoidal rule and Simpson's rule, and two formulas for their error terms. For trapezoidal rule, it's b minus a over 2n. The coefficients are 1 at the beginning and at the end, and 2 everywhere else. And for Simpson's rule, the coefficients are 1, 4, 2, 4, 2, 4, 2, and it ends with 4, 1. And then we have b minus a over 3n instead of 2n. And then the error terms are these, which you will be given these error terms. So that brings me to the end of this video. I will see you in the next video.